Cool. All right, thanks everyone for coming and voting for my talk. I really hope you like math, because half these slides are math. But I mean, I'll walk through the math. It's not that complicated if you just abstract it. Anyway, so the scheme is, the talk is about anonymous credentials through modern cryptography. So the agenda for today, motivation, why we want anonymous credentials, and why we want these kind of primitives. A bit of a crypto crash course about, because this stuff is based on elliptic curves, so little security crash course on elliptic curves, then a little bit more into depth on ring signature cryptography, how that's actually constructed. I've taken, I've actually implemented this stuff, but either way, I've taken a paper and I've turned it into pseudocode. I'll walk through the pseudocode. You don't have to understand the math, but I'll share these slides after. And my slides are usually really information dense, so you can read them after. It's not like a bunch of pictures. You're like, oh, what does I can't remember what this guy said. Then we'll go through the credentials scheme, using the ring signatures for credentials. And then after that, extensions of I2P for the real implementation. I2P being an invisible integer project. It's like Tor, but darknet only. So a little bit about me. I'm lead engineer at a company called Clearmatics, and I work on distributed systems and cryptography. So blockchains, but more than just blockchains. I'm mostly a software engineer by trade, but with heavy personal interest in mathematics, cryptography, and security. I'm heavily involved in the cryptocurrency and peer-to-peer community. I'm passionate about giving non-crypto devs the knowledge needed to use modern crypto. Use it, not implement your own. It's very different. You can see, you can take the libraries and use them to make your own schemes as long as you understand what the primitives give you. Don't try to roll. Never, don't roll your own scheme. Even I wouldn't do that. I take schemes from academic papers and I implement them. I only come up with schemes that I really understand. Also, cryptography is my life. It's really great. You can see from my T-shirt. I'm really passionate about cryptography because it's the only field where you, the defender, can outmatch any attacker if you use this crypto systems properly. No other field can I take a calculator and, if I know how to do the math, just, derive a public key and sign something, and then it takes an attacker, hundreds of billions of dollars to even try to break my key. It's the only one where the attacker-defender ratio is just ridiculous. It's not even worth it for you to get the attacker to try to break your crypto system if you actually use it properly. So again, we'll start with the motivation for this talk. So why would we want anonymous credentials? And by anonymous credentials, I mean not like anonymous password username. I mean, I give you something, and then you can use that like a key, and you can use that to authenticate yourself, but I don't know. All I know is you use the key, you use a valid key, but I don't know which key you used, or which credentials you used. So voting, for example, right? So you can give each key, a key to each key holder, well, to each voter, eligible voter. So you go to the embassy, like Estonia does this. You can get a little cryptographic key, and then you're entitled to one and only one anonymous vote. They don't use it for voting, but they're the only country that has EIDs right now. Payments, this is used in cryptocurrency, ring signatures, so you pay from a group instead of paying from an individual address. So you obfuscate or hide really sender-recipient links. Leaking secrets, whistleblowing. This is actually why ring or group signatures were created initially. I'll go into a little bit later. And also, if you construct the scheme properly, if you're a little bit creative on how you use this, you can use truly anonymous but rate-limited resource access. So that's what this talks about. And I have an implementation. I'm not sure if we get to the demo because there's a lot of slides and they're all very complicated, but we'll see. Either way, I'll put the source code up on GitHub, and I'm also doing a paper on privacy enhancing at the Privacy Enhancing Technology Symposium next year, which with a full formal proof of all this stuff. So yeah, this is the topic of the talk today. So let's go over this. So what are ring signatures exactly? So the concept is first introduced in a paper titled "How to Leak a Secret" by two of the RSA authors and some other guy. So it concerns using keys in a group instead of using them individually to prove you have a private key from the group as opposed to proving ownership of a specific key. If like normal EC-DSA, elliptic curve signature, RSA signature. If I give you a signature, you have to know which public key that signature is associated with. Otherwise, you can't verify it because it's like one-to-one correlation. But this allows you to have like a set of keys, like 10 keys, and I sign. And given the ring of keys, the group of those 10 keys in the signature, all you know is, yes, you have one of the signatures, but I don't know which one. And nobody, like if you don't have a signature from this ring, you can't forge it. It's anyway, I'll go into the math a little bit later. So yeah, it's it's very useful for whistleblowing, which is like which is how this concept was first introduced. It's if each public key in the group belongs to like a government official or like a journalist or somebody with privileged access to information, the official can leak some classified data proving that they are indeed a government official. So look, I have one of the 10 keys that only belong to these 10 politicians, but without outing himself individually as the whistleblower. Yeah, so you work at a bank or in the government, whatever. They're like doing some other crazy NSA stuff. And you really you're like really morally opposed to this, and okay, you can like attest, yes, look, it's one of these people, and they would truly have data access to that, but you have no idea which one it is. Cryptographically, you have no idea. It's just very secure. This is not like this is not magic experimental crypto. This really only uses the same security assumptions that elliptic curves use. So if you trust elliptic curve signatures, this is not much of a stretch. And, elliptic curves have been around for like 35 years now. They're fine. So he's like, ooh, a little stylization of what a ring signature looks like, but I'll go through the math. So ring signatures are a type of zero-knowledge proof. So if you've never heard of zero-knowledge proofs, what it means is basically I want to prove X and only X. I don't want to reveal anything other than that one bit of information. So you don't leak anything about the secret other than the fact that you have the secret. People always use really crazy analogies, but I like this better. So a simple analogy here would be I choose a card from a deck of cards, so if your standard 54-card deck, and I want to prove to you that it's a red card. Now, obviously, if I just show you the card, that's easy proof, but it's like showing you the private key. That's pretty stupid. It reveals more than just the color, like the suit and the number, and whatever. And the position in the deck as well, if I do it in front of you. But if on the other hand, I just take my card aside, like take my right card, put it on a pile here, I go through my 53 cards now, and I flip up, and I reveal to you all the black cards in the deck, assuming that I follow the protocol correctly, like the deck has 22 red cards and 22 black cards, however many cards are in the deck. I've proved to you that the card I've set aside is a red card without proving anything else about the card, without leaking anything else about the card. So there's many different types of zero-knowledge proofs, but specifically the zero-knowledge proof in ring signatures is called zero-knowledge proof of set membership, meaning that yes, I prove to you that I am a member of the set, strictly, I am a member of the set of private key holders associated to these public keys, but I don't prove to you anything other than that. I'm just proving to you that I am a set. The signature just proves to you that I'm a set member. So let's go through a really quick crash course, and I explain to you the properties of elliptic curves from a very abstract level, without going too deeply into how these operations go. But the elliptic curves has a special property that other cryptosystems, or I guess primitives used for signatures, don't have. So mainly it's homomorphic and commutative operations. What does that mean exactly? It means we can perform additions and multiplications on the public key without destroying its relation to the private key. So in mathematical terms, you can perform a morphism which maintains the group structure. So it's an isomorphism. Not to say oh, look, I can just take the public key, add a bunch of random crap to it, and then assume don't do anything else, and give you the public key with a bunch of random crap added, and magically I still have the key to that. No, you have to perform the same operations of the private key, but this doesn't work on RSA, because RSA is the security model is on factoring primes, and the modulus has to have certain the exponent is very specifically related to the modulus and the other parameters that you give in the signature. If you mess around with the public key, you have to find a totally new exponent. There's not an isomorphic map in there. But with elliptic curves, there is. And so it allows all this cool stuff. So security crash course, what security do elliptic curves provide? It's on RSA. It's pretty easy. I guess most of you know, RSA is really just based on the hardness of factoring composite large numbers and finding coprimes. So the security in elliptic curves is not based on that at all. It's based on discrete logarithm problem. So what's a logarithm? If I have a to the power of x and I have a result there, the logarithm of if a to the power of x equals y, the logarithm of y given base a would be x, right? So it's reversing exponentiation. Given y equals gx, y is the result of this operation, it's hard to recover it's hard to recover x, which is the private key. So remember, in both RSA and elliptic curves, we deal with integers on modular groups, meaning the operations wrap around, with clock arithmetic. If 24 hours, if I'm at 2 o'clock and I add 12 hours to that, I'm at 2 a.m. I'm not at 2600. Because it's a modular group, you don't have divisibility. So that's really, if you really want to have a very, very abstracted view of these levels of these kinds of security, is that because the operations wrap around, if I do an exponentiation, which on this number is very big, it's 256-bit integers, and the group generator here is an elliptic curve point. But anyway, it becomes a really big number, so the exponentiation as you're adding it's going to wrap around a lot of times. So you can't divide because once it wraps around once, you have no idea how to undo the wrap. So this is that's a discrete logarithm problem, and a lot of crypto is not really proven. But after 30 years of differential cryptanalysis, we're pretty sure that it's fine. If discrete logarithm problem is broken, a lot of this stuff is broken. So some of the properties of the group, to put them concretely, the G here, so you take a group, you take elliptic curve points, like this, x is 54, y is 243, and you multiply that by a scalar. And that's that's how you get that public key. Private keys are scalars, integers of the underlying field. So the field is again like a modular group. So one fun property about elliptic curves is that a 256-bit key, elliptic curve key gives equivalent security to it gives the same security as a 3072-bit RSA key. So the keys are much, much smaller, which is important as well for these kind of signatures because ring signatures are big. They have a lot of side information that you have to generate. And it's also kind of why if you're in the cryptocurrency space at all, why Bitcoin and whatever have taken off. It's basically it only was made possible because of elliptic curves. If you have to use RSA for this stuff, again, there's orders of magnitude more information you have to store because the signature is just so much bigger. It's so much slower to generate RSA signatures and so on and so forth. Anyway, so here's a really cool property, is the homomorphism between the private key and the public key. So if the private key is x and the public key is g to the x, then the private key of public key times k, like a random number k to the x, is x times k. So this is actually used for stealth addresses in Bitcoin. If you don't know what that is, don't worry about it. But basically, what this means is that if I give you my public key, you can generate a random number. And that random number can sort of be seen as a side private key. Generate a public key from that side private key. Take the public key, my public key, and the public key you've just generated, add them together, create a new public key, and send me the world. This doesn't even have to be secret. Send me k, the side private key, and and this gives me the private key to our combined key. So it's an interesting way to even do anonymous, uncorrelatable signatures because you can encrypt a message with the scheme. You can encrypt a message to me in a way that only I know that you encrypted it to me, and nobody else knows because they cannot reverse a discrete log on this. So yeah, it's like, if you abstract it in this way, basically just see all operations you could do on integers, discrete integers, like no floats or anything. All the operations you can do on integers, you can do elliptic curves, but division, you can't divide. That's what makes the discrete logarithm problem hard. You have the brute force. And for the people who sometimes worry, like the curves maybe not safe. There's like all that stuff about the NSA, blah blah blah. Not really, because for a 256-bit field, counting from 1 to 2 to 256, just counting, not even generating signatures or trying to generate keys, takes more than the lifetime of the universe, even if you have a sun-sized computer that's like theoretical max efficiency. Oh, and even with quantum computers, if you use this right, it still doesn't really break it. Quantum computers aren't like some magic pill. You need to have a quantum computer that's at least 256 qubits to break 256 EC keys, but that doesn't immediately break it. It doesn't give you some magical oracle that just immediately gives you a private key from a public key. It takes the square root of the difficulty. So 256-bit keys give you 128-bit security. If you have a quantum computer of 256 qubits, you have 64-bit security, information theoretical security. But that's still not easy. Like to break a 64-bit key would still take many years of computational time. So even if the government has like very powerful quantum computers, they would only be able to use them on select keys. They can't just like swipe or sweep over the entire set of all keys that are used and like pretend that they're going to get anything. So quantum computing is not the magic pill everybody talks about. Anyway, so let's take a concrete example, and here's when we start going into some math. But I'll explain this thoroughly. So as a concrete example, let's take Schnoor signatures. So this is not actually what's commonly used. Commonly, you maybe hear the term ECDSA, that's a signature. So Schnoor was patented. So people haven't used it until recently because the patent just expired. Schnoor is amazing. It's like the most intuitive way and simplest implemented way to do signatures on elliptic curves. Because it was patented, somebody had to come up with ECDSA, which is like trying not to do what Schnoor does. And it's really fucked up because of that. It's a horrible algorithm, but Schnoor is what we should all have been using if patents weren't like fucking up the world every day. So they provide zero knowledge proof of knowledge of the exponent, right? So I'm proving to you that I know x in g to the x without giving you anything else about it. There's a special property here that if you pay attention, you can clock onto, which is very interesting, right? So this means a signature reveals nothing at all about the private key. It does not provide an attacker any information for brute force. So even if I had unbounded computation, if I wasn't a polynomial time bounded attacker, brute forcing the entire state still does not tell me which key you used. Like there's no way to be 100% sure. It's like they're indistinguishable. So here's the math. So this is like simulation game in cryptography. Normally you replace it with hashes, and that's how you do signatures. But like walking through this is real quick. So generator. By the way, generator is like always public. Just like the generator in Diffie-Hellman or RSA, the generator is like 2. Here the generator is just some big number, but it's a public number everybody knows that. So we take the generator and raise it to W, which is like a random number. So and then we get like a big W, which is kind of like a pseudo public key. So Alice, I'm Bob, and I have my private key, and I just generated my W. Both these numbers, X and W, are like secret. I never reveal them to anybody. So Alice has my public key, which is just G to the X. So which is the public key to my private key. So she already has this before we start the simulation game. And before we start the simulation game, I already have X, and I just pick a random Y out of the blue. So I send Alice this pseudo public key. So now that this is called the commitment phase, and now that Alice has the W, she says she's gonna like try to generate a challenge that must verify given W, right? So I've committed to W, I can't take it back. So she picks a random number, again, just C, and sends it to Bob, me. Now I do this little operation here, which I take W, my pseudo-private number, well, pseudo-private key number, and I subtract c times x to it, and that's r. And then I send r the response to Alice, and then Alice checks, oh, does g to the r times Bob's public key times the challenge that I gave him equal w. So that's like the simulation game. And if you like spend a little bit of time looking at the thinking about the math, you can see how the signature works. It's actually quite simple. If you just pretend these are like, don't even pretend that we're doing anything on elliptic curves. These are just like normal numbers. You have g to the r times public key, Bob's public key, times Alice's challenge is w, right? Like the big commitment that I sent Alice. And if you expand it, remember that the public key is just g to the x. Yeah, the public key is just g to the x, right? So let's swap g public key with g to the x, and then this just becomes g to the xc, and then r, the thing that we're raising, the thing that Alice is raising to check for the equivalence, is again just w minus cx, and I've just rearranged it here to make it more simple. So w minus xc, w minus cx, and w minus xc are the same thing. Cx and xc. Yeah. So if we like reduce this algebraically, these two things cancel out. Just because of laws of exponents. So g to the w minus xc times g to the xc cancels out. So we just have g to the w, which is again w, right? So only if I have an x can I cancel that out after I've already committed to w, right? Only if I have the private key to my public key, because otherwise I wouldn't be able. I just don't have the number available to cancel that out. And again, we can't do division, so we can't get this number out of nowhere. So now there's an important property here that, like, there's a reason we had to do this simulation game in order. If you just forget everything I just told you, and you just like look at this equation here, if I just take this here, and I just pick a random r and a random c, remember that Alice never gets a little w or a little x. If I just pick a random r and a random c, literally out of the blue, I can create a valid w, right? So I can create a valid signature if Alice doesn't see me commit to w first. Because I can create a valid signature by just picking random values out of the air, if I don't have this commitment phase first, this signature provides no knowledge about the exponent other than, it provides no knowledge about the exponent at all if I don't have the commit phase. Giving the commit phase, Alice can force me to play the simulation game properly, such that, I'm not cheating and I haven't picked out random numbers that like coalesce. So, in normal functions, in normal signatures, this is called an interactive zero-knowledge proof. So Schnoor is non-interactive zero-knowledge proof. So the commitment is normally replaced by a hash function to force WC causality. So because the hash function is, I can't just pick a random C out of the air and then be like, oh, what input of the hash function gives me C, right? That's the whole point of a hash function. You can't just have like an output hash and then like magically take the input that gives that out. So you have to pick W to compute GW before having C. So that sort of simulates the Alice's commitment. But yeah, just really focus on this fact that if we don't follow this protocol in order, and if Alice doesn't see me commit to big W first, I can generate infinite signatures, right? So if we use the interactive version of the protocol, or even the non-interactive one, these signatures are forgeable if you don't follow the protocol. But they are not forgeable. But they're still sound, as in like you still have proof if you follow the protocol correctly. You have the proper proof if you follow the protocol correctly. So they have that security guarantee, but there is zero knowledge. So that's like really the simplest type of zero knowledge proof of an exponent. So you'll see some of the similarities. I mean, I'll share the slides later on, or I'll share it on Twitter. You can follow my Twitter or look at my Twitter. But this is just remember this equivalence relation here. So here's like the math for the ring signatures. I don't expect you to understand this, but I've turned it into pseudocode later on. So like if you can kind of tell, the ring signatures are really just an extension of the original zero knowledge proof. So this whole part here can be done by anybody, right? So we have the simulation game that can be done by anybody. The only part that requires you to have the real signature is this, because that's the only part that like really relies on CX. I mean, other than this is just a tag. We'll talk about that later. But you can see here, right? There's a zero knowledge proof where we multiply all of these pseudo public keys, pseudo commitments together, and make it so that when hashing them, the sum of all the commitments must equal the hash of all the commitments. So I mean, yeah, it's a little bit hard to follow. Again, you can read this later on, but this is the important part. You see, look, R minus CX, and this is the same as here, which is W minus CX. Here it's called the witness. There it's called the random commitment. But the zero knowledge proof that's in the ring signature is exactly the same as the zero knowledge proof that's in this normal signature, except for you add it to all the other pseudo commitments in the keys. So yeah, I mean, yeah, I guess it's hard to follow this stuff on a presentation, but this is like if you can't understand like cryptography maths, this is a little bit easier to follow through in your own time. So if you spend a little time doing drawing this by hand, and just as for some notation, if I do A to the N, I just mean concatenate all these. So take A1, A2, A3, and when I do H hash, this just means concatenate all these variables and return me the hash. So you can see that similarity there between generating that zero knowledge proof. And because I don't know, as a third party after you've done this protocol, I don't know which one of the keys you used. Again, because the signature generated here by not having the key, and just the signature generated here by having the key are indistinguishable from each other. I only use like a little bit of a hash pre-commitment here to make sure that I do have to have one of the keys. But after I provide you the commitment hash, the commitment scheme with the hash protocol, I just have no idea which one of the keys you use to generate the real signature. They all look indistinguishable to me. And again, remember the simulation game. If I just pick a random C and a random R, I do get a valid signature W. If nobody forced me to commit the W first, and it's the same here. So where I don't have the keys, I just create bogus signatures. This is just a little bit of an extended way to generate those bogus signatures. But you can see that these are just random numbers modulo Q, and their commitment is just a random number modulo Q. So we'll stop with this for now. So it's not that hard to understand, but you can review it later. So if you extend the ring signatures, so with this sort of some math, we can make our ring signature scheme allow us to check if somebody has signed twice, but we still never know who exactly signed. And how we do this over here, this is tau, the tag. I take the hash of the ring and the message, and this is a special hash function that doesn't hash into a number. It hashes to an elliptic curve point. Sorry, no, actually, this hashes to an elliptic curve point. I take the curve point, and I power it by my private key. And that tag is always going to be the same for the same message in the ring, right? But again, it's irreversible because we have the same issue. I can't reverse the streak log. So that's what that tag is. That's what the math. So if we follow this protocol and I construct the hash this way for the kip indent, yes, I can tell, yes, you signed twice, but I don't know exactly who signed twice. So no matter how many times you sign, I'll just take one of your signatures, but your security is still safe if you accidentally sign twice. So now this becomes more useful than leaking a secret. For a specific message, like 1, 2, 3, we can ascertain that one and only one member in the group signed that message for a specific signature. Or if you wanted to have like a voting protocol, you can say, look, I have the message of 10 keys, and if I have a signature from one signature here and another signature here, I can compute them. I can compute the tag, and if they're different, it's 2 different people who signed. I still don't know who signed though. I just know 2 different people from the set have signed, and nobody double signed. So yeah, this allows us to use a scheme for anonymous voting, private transactions, and the topic of this talk, which is the anonymous credentials and rate limiting. Okay. So here's the simplest construction where you could use the scheme. Say we have a ring of public keys R stored on a server that's behind an anonymized network like Tor or ITP. If you have ever ran hidden services, you know that, especially if you're running a forum, one of the huge pain in the ass is getting flooded, because again, every single IP every single user looks like they're coming from localhost, right? So you have no idea. I mean, unless you like start doing really tricky things that like you shouldn't really be doing, and people shouldn't be leaking if they're using an anonymous site where it's like, oh, let me look at the user agent and the latency and blah blah blah. But assuming that the network is proper and you want to like go through all this crap, you just have these massive flood problems where like one user can totally like make your forum or your I don't know, your website unusable because they're just flooding it consistently. If you ban them, you ban everybody because they're indistinguishable from everybody else. So for each epoch, so epoch is like a segment of time. So every 10 minutes or any 10-minute stretch, our server provides a random message m. So for from 1 to 1:10 p.m., the message m is like ABC. From 1:10 to 1:20 p.m., the message is XYZ, right? Whatever. So it provides a message that participants must sign in order to submit a post from a server. So they take the message, they sign it, and then they they attach their post like alongside it. So it's like, look, this poster is allowed to submit because they can generate a signature for this epoch. So this in essence limits each participant in an anonymous manner to posting a message every 10 minutes. While each participant is completely anonymous on the network, so while each participant is completely anonymous on a cryptography and networking level, for any one message m, they can only sign once as double signs are detected. So the important limitation here is this following: the signature is specific for the message ring computation. Like as we saw earlier, like this is how the tag is generated. So if either the message or the ring changes, as in like if I add a participant into the ring, like you can now you can double sign again, because now it becomes indistinguishable from the other ring. So there's an issue here which has some privacy implications, right? But let's just walk through like it really quick. So the server has like a pre-populated list of public keys. This could be like a guy that has invited someone. You have like a round where people can just request a key, and then after the day is done, you have this key. Then you can use the keys the day after, whatever. So anyway, in whatever way we do this, we have the set of public keys that the server has so that's fixed. It's not going to change, and the user has one key from here. So the user generates a signature, sigma 1 over, and by the way, there's like random components in these signatures. So every time I generate a signature, it's going to be different except for one particular piece, which is a tag. And the tag is always going to be the same if R and M are the same. So it sends the server with an action, like, look, I want to post this post like hello world to the server. The server is like, great, I see that given sigma, you do have a key on this ring, I just don't know which one. The server replies with success, computes unique tag from signature, and stores that tag into the database. So like, this tag can never be used again. So if the user now generates another signature, every single parameter of the signature is completely different, except for one parameter, which is a tag, which can be which you can compute to be the same, because they've just signed over RM1, it's the same. The server detects the tag in the signature the same and rejects. So the user is still completely anonymous. They're just prevented from signing more than once per epoch, right? So it's just, in essence, they're prevented from submitting more than once every 10 minutes. So to get around the limitation that we described here, where we can never change the ring once we set this up, the simplest scheme would be to only allow additions to the rings once per day, right? So this is like the naive way of constructing this. So to prevent spammers from accruing lots of keys to span with, or maybe I'll just like, I'll request like 10,000 keys, and then then I have 10,000. I can do 10,000 posts every 10 minutes, right? We haven't solved anything there. So additions to the ring can be governed by the same protocols. So each participant that currently holds a key is allowed to anonymously invite one participant per day by submitting their signed public key to the server. So I take my private key and I sign a signature, and I sign like the message, and then I append that message to a public key that I want added to the ring. And then every day the ring is rotated. So, but I don't like this though, because there's some privacy problems that remain here. So of course, if today, so this is like when we get into like why anonymity is really hard. You have to really think about this stuff. If today I have ring R and it has n keys, like 100 keys, and tomorrow I have the same ring and one extra key, so 101 keys, the new key, or the new user, can only have made posts from that day onwards, right? There's no way that that key that was just added, like made a post yesterday because that key wasn't in there yesterday. So we leaked some information about participation. So a new user, like this key was added today, so any posts from today are only posts from today onwards can be attributed to this key probabilistically. Posts from yesterday cannot be attributed to this key, right? So you have some side channel leaks there. And if we never remove keys, the oldest keys that are in the ring will be the most represented in the posting history due to having had more chances and more time and more chances to post, opening up some statistical analysis attacks. Like, the people who have been in there the longest are like the ones with the most posts, everything else equal. Furthermore, the invite systems for keys isn't really a perfect fit for honest networks. We can do better. It doesn't really make sense. Like, imagine if Tor or I2P were invite only. Like, you couldn't spin up a node if you weren't invited. Like, it's not really conducive to these kinds of communities. So what can we do? So turns out we can actually reduce the privacy issues to the best case, the best anonymity that the underlying peer-to-peer network provides. So I'll choose I2P here because of its active routing model. Unlike in Tor, each I2P router must also relay traffic. Since I2P is darknet only, you're only ever relaying encrypted traffic to another I2P node. So it's not like Tor, where if I force you to be an exit node, then you get like the government knocking on your door 2 days later because somebody's like, hacked the DNC or whatever through your Tor node. So I2P is darknet only. It's like if you ever use hidden services on Tor, like those are completely end-to-end encrypted, and they use a relay network internally. So like if I'm a relay, so there's 3 different types of relays in Tor. There's like middle nodes, guard nodes, and exit nodes. If I'm like a middle node on Tor, like all the traffic that I ever relay is encrypted. So I2P is like Tor, but only darknet mode. You can only ever like look at the internal hidden service sites, but also there's like a special property that allows us to use this scheme in the optimal approach, which is you just cannot participate in the I2P network unless you're also relaying other people's traffic. That's how they keep their indistinguishability. So I2P nodes already have public node keys associated that they advertise when active on the network. So an I2P node is called an I2P router because it routes other people's packets. When I join the network, I broadcast the network like, hey, I am node X with public key whatever. Please, use me as a relay if you want. And so you have to have bandwidth symmetry in I2P. So if I want to send a request to a server to get their packets, I kind of have to wait for a similar request to come in so I can bundle it. Obviously not 100% like that because otherwise nobody would ever be able to send anything at all. But you have to keep this kind of equal symmetry. You can only shoot out what you take in. So because of this protocol rule, any packet you send out is indistinguishable from a packet that you're also relaying, right? So the nodes use these keys to form unidirectional multi-hop tunnels. Just like in Tor, there's multiple hops, but unlike Tor, they're not bidirectional. So my request outwards can take a completely different tunnel than my reply, right? So which also gives you better anonymity. So they have, and also it's got bundle encryption similar to Tor. Maybe I send to this node here, and then that node decrypts, and then that node knows where to send, and so on. It might as you see here, it might actually loop it back to me, from PK1 to PK4 to PK3, and actually loops back to me, and now PK2. So I have no idea. So to a passive observer, you have no idea whether you've just relayed a packet or you just use your own packet. Or issued your own packet. So to send or retrieve traffic at all, you must be publicly reachable on the network through one of these keys. So I2P router keys, unfortunately, they use algum keys at the moment. It's not the same properties as Elliptic Curves. It's technically possible to do this with algum. There's only one paper on it. It's behind a paywall. There's no security analysis on it, so I'm not going to use it. But we'll just assume this, and there's not going to be a demo for an I2P TL scheme unless I roll on my own I2P, or I convince the I2P devs to include AC node keys. We'll see, because there's 2 guys that work on I2P, and they don't have a lot of resources. But so the I2P router database, it's similar to Tor. I2P has a list of nodes, but unlike Tor, it's a distributed hash table. there's a fun fact. Tor is actually centralized. There is a centralized point in Tor. It has 8 to 12 central directory servers that keep the list of guard nodes, relay nodes, and relay and exit points. If those servers go down, Tor stops working unless you know how to hard code relay addresses manually when bootstrapping. There's a little fun fact that few people know about. So when hosting a hidden service or an EEP site on I2P, you can know when the node key of any router is interacting with your service. You can know the node key of any router is interacting with your service, your hidden website, because they've encrypted a packet to your EEP site address, which is just the node key, right? So maybe you can notice here how big that scroll bar is. I2P addresses are not hashed like Tor addresses. This is just the entire public key, and that's how nodes find each other, by public key fingerprinting. That's a very big key. This could be because it uses algum, right? If it was like elliptic curves, it'd be a lot smaller. Whatever. Anyway, so how can we extend our ring signature to the additional security that the underlying network provides? So our ring R can simply be the set of node keys we currently see live on the network. So it's the whole active network that can reach the ring authentication server. It leaks no additional information because obviously node keys aren't live on the network, can't communicate with the EEP site anyway. If you were scanning the network and keeping track of it, you would get no less and no more information. You get exactly this. We leak exactly the same amount of information as the underlying peer-to-peer network. Plus, by real time, with real time, I mean epoch regulator to update the ring every 30 minutes. If we remove the keys as the I2P routers disappear and are no longer reachable, we stop long-term correlation attacks. So for today, the ring is completely different from tomorrow because the nodes today are completely different from the nodes tomorrow. Also because I2P routers cycle their keys after a while. So finally, because now acquiring a key necessitates building deep circuits into the network, it also solves Sybil attacks, because each key requires a certain amount of bandwidth to maintain. So if you are not aware of the Sybil problem, it's like from the terms from a movie, but basically it means let me appear to be the majority of the network by just spinning up a lot of nodes, generating a lot of keys, making a lot of accounts. If there's zero cost to creating a new identity, then there's zero cost to DDoSing the network, right? Because, but actually, we solved the Sybil attack because maintaining a well-connected I2P router is not zero cost. It requires a certain amount of bandwidth, like 200 kilobit up and down. It requires long-term commitment to the network, a lot of relays, and all the nodes kind of have reputation with each other, just like in Tor. So if your node is a real dick and drops packets all the time, you're just going to get blacklisted from the network. So making 100 identities is basically equivalent to owning 100 connection lines. So we solved the Sybil problem. So with the construction integrated in the network's peer identity, we've been able to devise a scheme where we don't suffer any loss of privacy whatsoever. Your users can be rate limited if you wish, but beyond that, nothing else happens to the privacy. We have the same privacy as a totally anonymous I2P or Tor. We gain anti-spam capabilities. Authentication is not only anonymous, but permissionless. You don't need to be invited into this ring. The ring is just constructed based on the node keys. And we gave the key identities a cost, which is the cost of being an active relay. So yeah, cryptography is great and magical. It can do so many amazing things if you really understand a few properties about the underlying cryptographic primitives. Cool. So that's about the 45-minute mark. Any questions?